basin formation the same or different?
Okay, thanks very much, Amy. So Jim may have left the stage, but I'm continuing the Brown theme here. So I'll be discussing some work I've done, which kind of follows on nicely from the previous talk. So in this talk, I'm looking specifically at the formation of these very large basins, focusing on Mercury and making comparisons to the Moon. When we look up at the Moon and Mercury, we can see that there are many similarities between the two. We see that both have undergone significant volcanic resurfacing, both show evidence of volatiles at their poles, both have tenuous atmospheres, and both are very much covered in craters of various sizes. But what about the craters at the very largest sizes? So let's look at impact basins. Impact basins are impact craters greater than 300 kilometers in diameter. And on the Moon, there are between 40 to 50 of these basins. When we look at the very largest of these, those greater than 500 kilometers in diameter, there is around 6 to 10. Some are slightly more certain than others, but a number around 6 to 10. When we look at Mercury, when we look at, again, these basins greater than 300 kilometers in diameter, we again see that there's a number around 40 to 50. And then again, when we look at these largest basins, 6 have been defined as certain basins, and again, there are maybe a couple of others that may be possibly be basins. So this seems to match, a similar number of basins of this size on Mercury and the Moon. However, when you think about this more, there seems to be some kind of disconnect here. Mercury has almost twice the surface area of the Moon, and given its greater surface gravity, you would expect to have far more of these larger sized basins than it does compared to the Moon. Keller Professor undertook a study initially to map the basins on Mercury, and he too found that Mercury seemed to have a dearth of basins compared to the Moon. And he suggested 3 possible reasons for this. Due to the latest data from the Messenger probe around Mercury, he ruled out any observational effects, leaving behind a possible effect due to the formation of these basins or some later stage modification event, including maybe viscous relaxation. The aim of this study, therefore, was to numerically model Mercurian basin forming impacts and compare them to previous modeling of lunar basin formation, and directly trying to address the second of Facet's suggestions, that the difference is a formational process between the Moon and Mercury. To do my numerical modeling, I used the iCell shock physics code, which has been used to model impacts at a variety of scales over a number of terrestrial bodies, including impacts between planetesimals. This image is showing a typical model setup for my impacts. So here we've modeled Mercury as a fully spherical object divided into 3 layers, with a basalt crust at the top, a dunite mantle beneath that, and with an iron core at the center. The projectile is also modeled as dunite. And we varied the impactor parameters with the velocities between 15 and 50 kilometers a second, and impact diameter between 50 and 240 kilometers. Another important factor to consider is the thermal profile within Mercury. This is particularly important for basins, given that these impacts formed around 4 billion years ago, when the planets are likely to have been far hotter than they are today. So therefore, we took 2 thermal models based on thermal evolution models of Mercury, aged at about 4 billion years. Okay, so I'll just explain this first. So in a minute, I will be showing you a video on the left-hand side is showing you an impact into Mercury. The right-hand side is showing an impact into the Moon. So sorry if you could just stop the video and go back. I'd just like to explain it first. Okay, so yes, we have Mercury on the left and the Moon on the right. Both have the same impact diameter of 80 kilometers, and the impact velocity is both 15 kilometers a second. The left-hand side, so that's the blue and reds, are showing temperature, so blues are lows, reds are highs, and on the right-hand side is showing material, so crust is in the beige and the grey is representing the mantle. So if we could play the video, please. We can see that in the Mercury case, the opening of the transient crater and its subsequent collapse is far on a smaller scale than it is on the Moon, and this is primarily due to the gravitational difference between the two bodies. Okay, the next video will be showing that again, also with a continuation along to the full formation of the body, full formation of the basin. So if you could play the next video, please. So you can see that on Mercury, so that's the panels on the left, the transient crater produced is smaller, as is the uplift that forms after the collapse of the transient crater. We can see that on both bodies, the basin is complete or fully formed within about 90 to 120 minutes after the initial formation. So at least at a visual level, the formation of these basins seems similar, given the gravitational differences. However, we want to take a more quantitative approach to modeling these basins, and one way to do this is to use pi scaling relationships. So pi scaling takes a number of impact parameters, such as the diameter of the transient crater and the radius of the impactor, to produce a number of non-dimensional equations that can be used to model impacts of any scale onto any body. So this figure here is showing two of those. So we have pi d on the y-axis, which is a measure of crater size, and pi 2 on the x-axis, which is a gravity-scaled crater size. So the Mercurian impacts here are shown in the orange diamonds, and these match up well, or follow a similar trend, to impacts into the Moon, especially the Untitled Basin, which Jim talked about in his previous talk, and also match well with impacts based on laboratory experiments for the non-porous rock scaling law. So this seems that the Mercurian impacts at this level seem to be very similar to those on the Moon. But what about if we take a specific parameter? So let's take excavation depth, for example. So here I've taken the Mercurian impacts and divided them into two separate velocity ranges. So the triangles show impact velocities at typical lunar velocities. So these are impacts less than 25 kilometers a second. Whereas the circles are showing them at more typical Mercurian velocities. So these are impacts at greater than 25 kilometers a second. And I should note that the average impact velocity at Mercury is 42 kilometers a second, which is over twice that at the Moon. And as we can see here from the numbers, that the excavation depth diameter ratio at the higher velocities is greater than it is at the lunar velocities. So this suggests that given a higher velocity, the impacts on Mercury are excavating to a greater depth. And these numbers, or at least the ones at the lunar impacts velocity speeds, compare well with a whole suite of numbers that have been suggested for the excavation depth to diameter ratio from a number of analytical, numerical, laboratory, and fieldwork. Okay, so in a minute, I will ask for this video to be shown. This is forming of the largest basin on Mercury, which is the Caloris Basin. So again, we have temperature on the left and material on the right. So if we could cue the video, please. So again, we see an opening of the transient crater. We see this collapse with a very large central uplift forming, which then undergoes collapse itself. We can see a lot of crustal material has been removed from the center of the basin, and this material is overturned at the edges of the transient crater on top of the crustal material. We can see that there's a secondary uplift phase, and this uplift phase is slightly exaggerated by the two-dimensionality of the code, which forces or concentrates mass along the axis of symmetry. If we speed up the video for the second half, again we can see that this whole basin forming process is complete within around 2 hours of the initial impact. So things to take away from here is that the complete removal of crustal material from the center of the basin and the very high temperatures that are produced. But if we take a look at the crustal structure beneath Caloris, based on gravity data taken from the MESSENGER probe, we can see that Caloris has around 10 to 20 kilometer thick crust beneath the center of the basin. So how can this be how can the models possibly be related to this? Well, one possible reason may be due to the volume of melt that is produced in the impact, as Jim was alluding to in his talk for Untitled. So this figure here is showing melt volume on the y-axis and impact energy on the x-axis. for chloris-sized impacts, and these compare these directly to impacts that I've done for South Pole Aitken and Orientale. So you can see that the impact energy for chloris is on the same order of magnitude as that for South Pole Aitken, but produces around half an order of magnitude less melt. However, it's still producing on the order of 10 to the 7 cubic kilometers. So this is almost equivalent to the entire volume of the northern volcanic plains on Mercury. So you're producing a large volume of melt in just one single event. So it's possible, as Jim was mentioning in his previous talk, that this volume of melt could undergo some kind of differentiation process, forming a lower density crustal-like layer towards the surface, which, with gravity data, may be construed as being crust. So in conclusion, it appears that the dynamic phase of basin formation on both the Moon and Mercury are consistent with each other. However, on Mercury, due to its far greater average impact velocity, it has a greater excavation depth-diameter ratio. So therefore, the difference in basin size, number, and degradation state between Mercury and the Moon is therefore likely due to longer-term factors, such as viscous relaxation or younger volcanic resurfacing, than it is due to an inherent difference in the formation of these particular basins. And with that, I will end and take any questions. Thank you.
So Mercury being farther from the sources of projectiles, presumably the average impact velocity is higher than it is on the Moon. What is the average impact velocity at Mercury?
It's 42 kilometers a second. So it's over twice that at the Moon.
Hey, Ross, I have a question. So we all know that the core of Mercury is quite large. And I did see it a little bit in your hydrocode model, but how much of that do you think affects the way that the Mercurian basins are forming if your mantle is so thin compared to your core?
Okay, so it appears that the core doesn't really have an effect on the formation of the basin, at least in the area where the impact occurs. So the video I showed of chloris, you could see that the transient cavity doesn't quite reach the core, and chloris is the largest basin we see on Mercury. So we think that for the vast majority of basins, the core isn't being involved actively in the formation of the basins. However, it's possible that the larger basins could produce global effects. So maybe the core may have other interactions with, say, the passing of the shock waves. So that may affect the distribution or maybe the shock or fracturing things you find elsewhere around the planet.
And what about some of the different thermal histories? So I know a lot of your work has been doing models at different temperatures. So can you kind of back calculate by looking at some of these craters and say, okay, well, I have a pretty good idea of what the heat budget was of Mercury when this crater was formed? Is that something that someday could possibly be done with your models?
It's possible, yes. You really have to have very well-constrained parameters to be able to sort of compare those models to. Mm-hmm. So for example, with my modeling of South Pole Aitken, the Moon has a very large data set at high resolution that you can use to pick out and be able to very specifically constrain the models to kind of observations. So from that, you can figure out, for example, what shape the crust will be, where a particular objective would be. So looking at different thermal profiles for that, you can figure out what the best is. However, for Mercury, the data isn't as high resolution as is for the Moon, so you sort of have less constraints with that. But you can still have some idea of what the thermal structure is like. So at least in these initial models, it seems similar to what it was like at the Moon.
Okay, thank you. Any other questions? Yep.
Hi, Ross.
Hi, Phil.
On your chloris model, you've got a really hot, looks like you've got a really hot plug going down quite a long way. I just wondered, in the melt sheet modeling, felt like that would give you a nice heat source for a lot longer than if it was modeled as a sheet. Maybe that would keep it hot longer.
So part of the reason why there's a concentration of very high temperatures along the symmetry axis is again due to sort of the two-dimensionality of the code. So you try to look more away from that axis to see what the distribution of kind of the temperatures are. So it seems fairly stratified. So it does look like it's more of a melt. Yes, more of a kind of a melt sea that could mix in together. Yes. So it's not necessarily all hot right down the middle. Yeah.
Okay, thanks, Ross.